Hello again. See the screen?
Yeah.
Thanks. Okay, so this was a question from last time also, which is, again, a good question. It's not about proposing a new algorithm or an alternative to the current one, but it's rather a question about some aspect of the algorithm. So what if mark is first read and then set? And what this means that, in principle, if you have two threads, one of them is reading the mark flag, which is the contain, because this is the place where the mark flag is read. And then you have some other thread. So suppose that the red thread is trying to do contain. And this is exactly what I mentioned before the break. It reads the mark flag. And then after that, so it will first execute line 4. But before executing line 5, some other thread, say the blue thread in this case, will come and delete the cell. So what happens in such a case? In fact, I can tell you already here that this is fine, because this is also the linearization point. So once you have seen the mark flag and to be false, then this will be your linearization point by definition. And therefore, whatever happens afterwards, it doesn't matter, because you have observed this and you have recorded the result in B, and it's only B that you look at later. So let's see this concretely. So we have the red thread first, trying to check for contain 5. So now the red thread is active and doesn't call the locate procedure. It goes and searches using the while loop, sets the list, tries to find the correct cell. And this is what happens here. So C is assigned the value of head, and then do the while loop, go all the way and find the correct cell, which is 5. And now exit the while loop, and now read the C mark, which in this case is false. So this is false. Let's read the mark of the C cell, it's false, and we record the result and store it in B. So let's remember that now the value of B is false. So now we have read C mark. So now the red thread will become passive, and this will be the linearization point. And this is important. So it's important. So this also tells you that it's important how you define your linearization policy. So it's important that you define your linearization point to be when you do line number 4 and not line number 5. This can be already too late. But if you do it at line number 4, you know that your linearization point is now here, successful contain, unmarked entry with input key. So you have found the key, the entry or the cell with the input key, which is 5, which is unmarked. That is, the mark flag is 0. So this will be a successful contain. And not only that, this will be the point where I define my linearization, or this is my linearization point. So now the blue thread will become active, and it will change the value of C mark from the point of view of the red thread, because it's deleting. It's going to delete the node with value 5, which means that in particular that it will logically delete it. So remove 5 is now active from the point of, or the blue thread is active and it's trying to remove 5. Sorry. So it calls locate. Locate will find the right cells again, locks them, returns the pointers as usual. Cval is equal to E. Is it equal to E? Yes, it is, because Cval is 5 and E is 5. So this means that now, yeah, so this is the Cval. It is 5. It's equal to the input key, which is also 5. So now this is exactly the question. If I understand the question correctly, mark has been read and now it's set. So this is what happens. Now it's equal to 1. But now, and this is the linearization point, because the linearization point for a successful remove, which is what we have here, is that when the cell is marked, it's exactly that point. So this means that now we'll have our linearization point after the linearization point of the red thread, as you see here. And now we go ahead and delete the node physically, as usual. In fact, before that, it seems that the red thread now will become active again. But now you see that the value of CMark has been changed, but this will not be reflected here because the value of B has already been defined, which is equal to 0. So this condition will succeed. Because the C value, of course, has not been changed, and the CMark, which is stored in B, was 0. So this means that this condition will succeed, and this means that we return true. So this means that when the blue succeeds, the red exceeds, it gives back the value true. And now the blue will continue. It will delete the cell logically by defining n, and then redirecting the next of the p pointer here. And then we return true because we have been successful. Unlock the cells as usual, and then return R, which is true. Sorry. So this is the history we generated, and this is fine because first 5 was there. So when we did contain, it's true, and then after which we removed 5, which was successful also. So it's fine. So the crucial thing is that when you linearize, you should linearize when you observe the mark flag. And after that, it doesn't matter if some thread comes and changes the mark flag, because already you have made your decision and you have defined your linearization point before the point where the next thread, which is removing the cell, takes effect. It has its linearization point. Okay, let me see. Although this is correct, is the contain procedure ever useful here? I get back a true from contain, but a concurrent remove has removed it. The result from contain is, no, it's not useless. This is the very definition of linearizability. If you have two methods which are concurrent, then you can assume that this is what we said in the beginning. Then we assume that one of them can be before the other. You don't know which one will be before the other. So this will be useful. I mean, if you have, if the blue thread did not overlap with the red thread, then definitely the order, I mean, this is the first definition when we define the notion of converting a concurrent history to a sequential history. So we say that the intuition always is the following. If you have two concurrent calls, then you don't know in which order they occur. So whatever answer you return is fine. So if contain, so there should be one linearization of the concurrent history, which gives you the correct sequential history, which means that the contain is useful because if it did not overlap, then it will return only one answer, which is the correct answer. So if the contain terminates before the blue starts, then it will return true. On the other hand, if contain starts after blue has terminated, then the algorithm will make contain always return false. So again, if the methods, we had these two relations between method calls. If you have precedence, that's one of them precedes the other, then the result is well defined. If they are concurrent, then you don't know in which order they occur anyway. So this means that you allow both possible outcomes. So let me see. This means that we don't consider real. No, of course, we do consider real time, but we say that not really. We do consider real time in the sense that if some method terminates before the other one has started, then you should take the order into consideration. But if they overlap in real time, then you don't consider their order. So real time is relevant. In fact, in the sense that it tells you whether two methods overlap or not. So this is how they are, how real time is relevant. There is other criteria for correctness, which is like sequential consistency, where you do not consider real time. The only thing you consider is the program order. So you consider the order of operations per thread, and you can reorder things as much as you like, only that you respect the order of the calls as issued by the same thread. And there, real time is not relevant. So to answer your question, are there algorithms that intentionally try to place the linearization point as close to the return? No, I mean, you don't, by definition, you don't need this, Ahmed. And this is not correct always, as I showed in this particular example. In fact, in this example, the linearization point for the unsuccessful contain may be decided by some other thread, by what some other threads will do. And also, as you will see in the third assignment, I'll give you one algorithm, although although I'm revealing part of the answer, but never mind, in the third assignment, I'll give you an example of a simple algorithm, seemingly simple algorithm, where you cannot decide the linearization point unless you have the whole history. If you give you the whole history, then you can define the linearization point for each call. But you cannot define it in terms of how you execute the codes as we are doing here. And also there was some good question by mail. I think it was from Yusuf. And the question was, which was a good one, says that, well, I mean, how do we define a linearization policy formally? You see that, so in these lectures, these linearization policies are defined by saying that if you do this and that, then this is the linearization point. It's sufficiently precise for the purposes of this course. And this is the level of precision that's used in the book and also in the papers that describe implementations of these algorithms. So we will be happy with this kind of precision in this course. But if you want to prove formally that something is linearizable, then you have to define, in fact, you have to define a formal language in which you define your linearization policy. And this is what we do when we do model checking for these algorithms. But this is beyond the scope of this course. So for the assignments, you just define your linearization policies as I'm doing here. If this thread does this, then at that point, I define my linearization point, and this should be fine. Right. Okay, so any other questions? Of course, you can send me the questions, I said, even later. So otherwise, I will go to the Treiber stack algorithm. So remember that what we said up to now is that we are defining principles, and these principles are applicable in different settings. Like the things I defined for sets, they are applicable if you have skip lists, for instance, if you try to, instead of singly linked lists, if you have doubly linked lists instead of singly linked lists, but also for other abstract data types like multisets, as you will see in the second assignment, code assignment. But also some principles can be extended to stacks and queues. And now we, just to show you such an instantiation of the framework for stacks and queues, I will show two classical algorithms. One is the Treiber stack algorithm. So first, which implements the abstract data type stack. let's just recall the abstract data type stack very briefly. So we said that a state is a word over integers. We have two methods, push and pop, and these are the rules. Where push appends the symbol A to the head of the stack, and pop pops the value at the top of the stack. And then if you have an empty stack, if you try to do pop here, then you return a star. And then we gave some examples. Initially, the stack is empty, and then you can apply these rules. You can push 3 to get 3 in the stack. You can push 7, you get to 7 in the beginning, at the top of the stack. You can push 5, you get 5 at the top of the stack. And now if you pop the topmost value, which is 5. So in particular, push operations have input values, but they are always successful, so they don't have output values. And pop operations, they don't have an input value, but they have an output value, which is the value of the topmost element in the stack. And this is what happens if you pop 5. And if you pop 7, you just retrieve the 7, and then you remove the 7 from the top of the stack. And this gives you a trace, and this particular trace satisfies the abstract data type stack. So this you should know now. So now, one more paradigm that I will try to describe in these algorithms is what we call the lock-freeness. Now, lock-freeness in fact, it has two meanings. So these algorithms are lock-free in two ways. They are lock-free in the sense that they satisfy the liveness property of lock-freeness, which means that always you guarantee that at least one thread will progress, but also they are lock-free in the sense that they don't use locks anymore, not even inside the cells. Instead, they use an operation which is called the compare and swap, the CAS operation. And this is a very useful operation in concurrent programming. If you ask the architects or the people who are working with implementing programming languages, they say a CAS operation is much more efficient and less costly than a lock operation. So please use it whenever you can use it. And what's a CAS operation? So if you don't know it, I will just explain it to you in 1 or 2 minutes. So you can see a CAS operation as a piece of code which is executed atomically. So all these things that I'm writing here will happen in one step. And this can be guaranteed either by hardware or by the compiler. So a CAS takes a variable as input. It takes some expected value as input, and value which is called new as input. So 3 input parameters: x, variable, expected, and new, which are values. And it uses a temporary variable, local variable, which is called temp, which is an integer, provided that x, expected, and new are integers. Now, this can be instantiated to different data domains, but here we are working with integers, so all these are integers. So now, atomically do the following. Assign x to temp. Now check whether temp is equal to expected. And if temp is equal to expected, then assign to x the value new and return true, otherwise return false. So this means that you check whether x is, the value of x is expected, the expected value. And if it's the expected value, then you change it to new and return true. So this means that the CAS operation has been successful. Otherwise, return false. And there are both hardware and software implementations of this operation that is executed atomically. Like these are hardware instructions that perform this in Intel, in Spark processors. In Java or in C, you have things that are called compare and set, compare exchange, and these things you will use in the third code assignment, because I will ask you to implement variants of the Treiber and Macklin-Scott algorithms. So let me give you an example of the operation of CAS. So suppose that you have memory, and x is stored in the memory, so this is the value of x is 5, and I apply cas in this to this memory configuration. So now what the cas instruction does is that it looks at the value of x, whether it's equal to 5, the expected value. If yes, it changes the value to 7 and it returns true, all atomically in one step. So in this case, it will change the value of x to 7 because it was equal to 5, which was the expected value. If term is equal to expected. And in such a case, it returns true. If not, so if you try to apply the cas operation to this memory configuration, then it observes that the value of x, 7, is not equal to the expected value. So it just returns false without changing the value of x. So again, a successful cas operation or a cas operation is successful if the value of x currently is equal to expected. In such a case, it's updated to the new value and you get a return value which is true. Otherwise, you don't change the value of x and you return false. And this is all what you need to understand the Treiber algorithm. Now, what we do is that to implement the stack, we again use a linked list. Now not sorted, not necessarily sorted, but with the keys inside the cells, and then with the next pointers as usual, pointing to the next cell. Now, the content of the list reflects the content of the stack in the same order, from bottom to top. So 2, 7, 3, 5. And then you have a sentinel node, which contains the topmost element and which is pointed to by this global variable shared by all the threads, which you call top. So now we define the push and pop operations for Treiber in Treiber stack. The push operation is the following. So what we do is that we try to, or we add, we'll try to add the new node with the given key to the list. Remember, push has an input value, which is the key you are supposed to add to the list, to the stack, and make it the new topmost element. And you return a value. In fact, you don't return a value, sorry. You don't return a value because you are always successful if you terminate. And what you do is that, as expected, you create a new node and you make it point to the current topmost element and then make top point to the new node. So this is what we do here. So suppose that we have a push operation by the red thread in which you try to push a 4 to the stack. Then what we do is that we create a new node with the key 4, like this, and we call it n. So now what we do is that we try to add it to the list. And for this, we have this while true, this infinite while loop, which you exit. We exit if we have succeeded in adding the cell. Otherwise, we reiterate. So let's see what can happen, what can go wrong. Why do we need to reiterate to re-execute the while loop? So first, what we do is that we have this local variable t, which is a pointer, which you make it point to the topmost element, the currently topmost element in the stack, the one pointed to by top. So while true, attempt to add the new key, the new cell to the list. And we do this performing these steps. First, we make t point to top. So now t is pointing to this. And then we make the next pointer of the cell n point to t, or to top, like this. In fact, to t, because top may have changed, because some other threads may come and change top. And now this is the important operation. And indeed, the linearization point, as we see for the push operation, we do a cas. And what the cas does is that is the value of top still equal to t. This means that is there any thread which came and changed the value of top, either by inserting a new cell using a push operation or by removing the current topmost element by doing a pop operation. If you fail, you go back and perform another iteration of the while loop if this has happened. Otherwise, we succeed and we exit. So in this case, nobody has come. So we succeed because the value of t is equal to top. And in such a case, atomically, we change the value of top and make it point to the same cell point to my n. So this is what happens here. And you have been successful. And here, as you will see, when we define our linearization policy, this will be indeed the linearization point for a push operation when you succeed in doing your CAS. Again, so what we do is that we create a new cell, we let t point to the current topmost element in the stack, we check atomically whether the top element has changed or not. If not, then we succeed, the CAS operation will succeed, and we redirect the top pointer to point to our new cell, which is n. And now you see that if you look at the list here, it reflects a new content of the stack in which we exit, and we reflect a new content of the stack where we have added the 4 as the topmost element. Okay, so now why the CAS instruction? Why is it needed? And this we can see already if we have concurrent push operations. So suppose that we have the same scenarios before where we have the red thread trying to add 4 to the list, push 4. Now, we will have a new thread, which is the blue thread, which is trying to push a 2. And these methods overlap. So now both of them are active. The red thread will create its new node first, point to it by its n variable with the correct key, which is 4. And then it enters its while loop. And in doing so, it goes to the next instruction where it makes its t pointer point to top, to the same node as top. And then it defines the next of its of its new cell and makes it point to t. Fine. So now the blue thread becomes active. And now it tries to do its own push, but with a key which is equal to 2. It doesn't matter the value of the key because whatever you add it to the stack. So now it enters its own while loop after creating its new node with the right key, the correct key, which is 2. And then it enters its while loop and it does the same thing. So now t of the blue thread will point to top also. So now there is contention between the blue and the red threads. And the question is which one of them will succeed. So the blue thread continues and it defines the next of the next pointer of the new cell to be equal to its own t, which is the same cell as the one pointed to both by top and the red t. And it goes to its CAS instruction. Now it checks whether top has changed or not. Remember, this is what this tells us. Is top equal to t? It's t, which is the blue t. If yes, then the top has not changed. And in such a case, make top point to n, or to the new node, which is what we have here. So now the blue thread was successful, in fact. Now it can exit. So now the red thread becomes active and it does the CAS operation. So now it does the same thing. It checks whether t is equal to top, whether top has changed or not. And now the CAS operation will fail because t is not equal to top. They are pointing to two different cells. And then therefore it returns false. So if it had returned true, it would have exit. But because it returns false, it means that it will not execute the exit of instruction, which means that it performs one more iteration of the while loop. So this is what will happen. So this is the situation as we have it now. It's exactly the same as before. I just changed the figure like this. So you have a new content of the stack. The blue thread has disappeared. The red thread is still trying to add its new cell to the stack. So if nobody comes, it will succeed in doing that because it will put its T pointer point to top and redirect this pointer to point to top, etc., etc. But now, yes, this is what it's trying to do. It assigns to T the value of top, which is the same node as pointed to by top. And then it makes now its new node point to T, which is what we have here. And then it goes to its cast instruction. But before doing that, now the green thread will come and does the same thing as the blue thread did before. Create a new node with key 2, go to the while loop, define your local pointer T to point to top, define the next pointer of your new node to point to your T, the green T here. Do the cast operation. In this case, the green thread will succeed because the T is equal to top. They are pointing to the same cell, which means that the top now will be, the new topmost element will be the new 2. So now, if you look at the stack, it contains 2, followed by 2, followed by 5, 3, 7, and 2 again. Well, the red thread has not succeeded or failed again. So now it will try to do the cast. It will fail again. So you cannot guarantee weight freedom in this algorithm. In fact, this is one of it is lock free because always there is one thread succeeding, because the only reason why the red thread failed was some other thread came and succeeded in performing its operation. So this means that you have global progress, which is what we call lock freeness. So remember, lock freeness means that some thread will succeed, but you don't have weight freeness, which means that any given thread will succeed. So some thread may starve. So you don't have starvation freedom, you don't have weight freedom. Weight freedom and starvation freedom in this course are the same. So this is one of the disadvantages. It's lock-free, but not weight-free. It's lock-free in 2 senses, in fact. It's lock-free because you have global progress. One thread will succeed, at least one thread all the time. And it doesn't use any locks. Instead, it uses the cast instruction. In fact, this is like just a small refinement of the coarse-grained algorithm. So remember, in the coarse-grained algorithm, I can implement a coarse-grained version of the stacks, as we said before, by just putting a global lock and then letting only one thread manipulate the stack. Here, we are doing it slightly differently. We are putting a cast instruction and let the threads contend for the topmost element, which is more or less the same thing. So you see that what we are doing is that you may have several threads trying to become or to define the new topmost element in the stack. And this means that if you have a large number of threads that are active at the same time, these threads will manage to enter, but only one at a time, because the cast instructions will fail. So this means that you are not very efficient practically. There are other algorithms to implement stacks that will allow threads to operate concurrently, more concurrently, and therefore they are more efficient. But we will not go through them in this course. Okay, so this was a simple instantiation of a framework where we where we use cast instructions. So for the pop operation, it's in principle similar. What you do is that you do a while loop, and then you identify the top element of the stack and check whether the stack is empty or not. Because remember, for pop operations, we have 2 possibilities. Either the stack is empty, in which case we return the star constant, or it's not empty, in which case we return the topmost element of the stack. So here, what we do is that if the red thread is trying to pop, remember that pop doesn't have an input value. So you go to the stack and you take your local variable t and make it point to the topmost element of the stack, like this. And then you check whether this is equal to null or not. Null meaning that the stack is empty. And then in such a case, you return a star. Otherwise, which is the case here, you do the class operation. Now, the role of the class operation is the same as in the push operation, namely to ensure that the top most element of the stack has not been changed by other threads, either pop or push. So in this particular case, because there is no interference from other threads, the operation will be successful because top will be equal to t. And in such a case, you redefine the value of top and make it point to the next of t. And all this is done atomically, remember, and you get a value back, which is true, which means that the class instruction was successful. So all this happens atomically. Top will point to the next of t. The operation was successful, and therefore the condition of the if statement evaluated to true, which means that you enter the body of the if statement and return the t-val. T-val is the value that you should return as a pop, and this is exactly the key of the cell that you have just popped from the stack. And in fact, the success of the class instruction here will be the linearization point for a successful pop, as we will see later. And then after that, you exit. So now again, to illustrate the role of the class instruction, I will show two concurrent pop operations. And then on Friday, which is the next lecture, I will show you a mixture of pop and push operations, and I'll define the linearization policy. So if you have two concurrent pop operations, what will happen is that, again, we execute our while loop. As usual, we make the t, our local variable t, point to the topmost element for the red thread. And then we try to execute the class instruction. Now the blue thread will try to do a pop operation, and it will do the same thing. So pop, do enter your while loop, define your local t, the local variable t to be equal to top, which means that both of them will point to the same node, which is the topmost element in the stack. And now both of them are competing to remove this node. So again, you check for whether it's null. No, it's not. So now you do the class operation. Is top equal to t? Yes, it is. So if whoever succeeds in doing the class first will succeed. And in this case, I think it's the blue, if I remember correctly. So the top will be redirected to the next element, and we return t-val, which is the 2 here. And then you exit. So now the red thread will wake up and try to do its own class operation, and it will fail because it checks, compares top and t, and sees whether they're equal. And in this case, they're not equal. So this means that the if statement will fail, and you go back and perform one more iteration of the loop like this. Finally, for the empty stack, what you do is that if the stack is empty, it means that top points to an empty stack, an empty list. And when you do the while loop, you may, in the case you have an empty stack, t will point to the same cell as top, which is the empty list. And in such a case, you check whether it's null. And in fact, this is the point where you linearize, as we will see on Friday. And if it's null, you return star, which is what you should do for an empty stack. Remember that if you pop from an empty stack, then you should return a star and then you exit. So I don't think I'll have time to go through the linearization policy. What we will do is that, again, if you have questions, please send them to me either today or tomorrow. If you have any scenarios that you want me to go through, either send them today or early tomorrow so that I have time to make the slides. So otherwise, what I will do is that I will define the linearization policy for the Treiber stack, and then I will go through the Michaels and Scott queue algorithm, which is an implementation of a concurrent queue. And then I will go through one particular problem, which is interesting, which has to do with cell reclamation, that's garbage collection, in which if you are not careful, then you get some error due to the interference from the garbage collection algorithm in languages like C. And this is called the ADA problem. So this will be the content of the next lecture, which will be the last lecture. Okay, then. So thank you very much and see you on Friday. Bye for now.